Hey everyone, this is the third and final part of our review, in which we will examine the review article 3D printing of magnesium alloys in bone tissue regeneration applications, and summarize the discussion. I hope you will find it useful. And you can also find the online link to the article from the caption. First and foremost, we discuss properties of laser powder-based fused MG implants, their mechanical properties, their corrosion behavior, and of course their biocompatibility. A 3D printing process so precise it can build not just basic boxy shapes, but complex, finely detailed implants with specific porous patterns. That's the benefit of using LPBF. It can produce highly porous, non-prismatic structures tailored for things like orthopedic implants. By adding these porous layers on the implant surface, studies suggest we can improve how well new bone tissue sticks to the implant, known as osseointegration. Meanwhile, our own bones include three distinct cavities: haversian canals, osteocetic lacuna, and canaliculi that collectively influence how bone remodels and adapts. Porous implants mimic these specific spaces, letting nutrients flow so living tissue can thrive. This also lets engineers tune the implant's stiffness to more closely match natural bone, reducing issues like stress shielding, as we discussed earlier. When designing these porous components, we often talk about stochastic versus non-stochastic structures. One has an irregular random pattern, while the other's internal geometry repeats in organized unit cells. In either case, metal-based cellular structures excel in multiple fields: automotive, aerospace, chemicals, thanks to their lightweight nature, energy absorption, and thermal properties. Imagine trying to create a scaffold with complicated external shapes and intricate internal channels using traditional methods like casting or powder metallurgy. You could adjust some parameters to introduce pores, but at the end, results would likely be random and hard to control. That's where laser powder bed fusion shines. It can fabricate porous metals with a carefully designed outer geometry and an internal structure fine-tuned to match the rigidity of bone, reducing the stress shields often needed in manufacturing. You might wonder why not just use directed energy deposition, another form of additive manufacturing. The key difference is that LPBF typically uses a smaller beam spot, finer powders, and thinner layers, leading to higher dimensional accuracy and more precise details. It also works with higher energy densities, melting metal powders without needing sacrificial benders. Compared to electron beam powder bed fusion, LPBF's smaller spot size and powder particles let you stick more closely to your original digital design. There's also wire arc additive manufacturing. While it's great for certain applications, it can leave metal scaffolds too coarse for medical use, and its wire feed limits your alloy options. Plus, parts made via wire arc can have rough surfaces and higher degradation rates inside the body. Altogether, LPBF's ability to build near-net shape parts with intricate features and minimal material defects makes it especially appealing for creating magnesium implants that need to be both strong and biocompatible. When the magnesium implants are fabricated through this method, their mechanical properties improve significantly due to the formation of a fine, continuous microstructure during rapid solidification. The key to achieving the best results lies in balancing the powder particle size. Finer particles melt more easily and contribute to a smoother surface finish, while larger particles enhance mechanical strength, hardness, toughness, and ductility. Another crucial factor in LPBF processing is anisotropy. Meaning the material properties vary depending on direction. Since LPBF involves rapid cooling through conduction, convection, and radiation, the microstructure develops differently along the building direction. An implant built vertically perpendicular to the base plate experiences different thermal history compared to one built horizontally parallel to the base. To ensure optimal results, every aspect of printing process must be fine-tuned. Factors such as scanning strategy, base plate temperature, and build direction all play a role in determining the final implant properties. If the LPBF parameters, particularly laser energy density, are not precisely controlled, defects like cracks, pores, and metallurgical inconsistencies can weaken the implant. This is why selecting the right settings is so important. When done correctly, LPBF can produce magnesium implants with strong, reliable mechanical properties, which ensures they function effectively inside the body. And figure 6 comparison of tensile properties of different magnesium alloys, as you can see in the top corner, developed by LPBF and other conventional production techniques. Yield strength versus elongation. But when comparing LPBF fabricated magnesium alloys to their cast and wrought, whether rolled or extruded counterparts, significant difference in yield strength emerges. So you can infer it from the figure 6. Typical magnesium alloys designed for structural application generally have a yield strength exceeding 200 megapascal, with some reaching up even to 350 megapascal. However, despite their strength, LPBF magnesium alloys often exhibit extremely low ductility, usually below 5%, and in some cases they lack ductility altogether. This limitation makes compression and hardness testing essential for assessing their mechanical properties. But altogether, I can say, unfortunately, such poor ductility means that many LPBF magnesium alloys are not ideal for engineering applications. It is noteworthy that even when these alloys have fine grains, weak textures, and minimal porosity, their ductility remains insufficient. Several factors contribute to this. The rapid solidification process in LPBF creates high residual stress, so it directly impacts ductility. Additionally, in alloys such as AZ91, WE43, and magnesium gadolinium, intermetallic compounds tend to accumulate along the grain boundaries. This weakens the material, making these boundaries prone to localized failure. Many mechanisms, such as grain boundary sliding or the inability to transmit deformation through slip and twinning that you might encounter in materials engineering or university courses like ceramics, bioceramics, etc. So when these kind of failures occur, the material loses its ability to undergo plastic deformation. These are the main issues, but another issue is the redeposition of sputtered powder or vapor onto the sample surface during the fabrication process, let's say. This can lead to a weakly bonded regions or poor consolidation, further diminishing the mechanical integrity of the final part. So let's go to the table 3. This table presents a comparison of LPBF-processed magnesium and its alloys. Energy density varies significantly, as you see, across different magnesium alloys, and definitely influences their properties. As an example, the AZ91 alloy demonstrated superior tensile strength but less ductility compared to the other variations. Pure magnesium exhibits higher corrosion rates than some of its alloys. Overall, the mechanical properties improve with alloying, with AZ91 displaying some of the best mechanical performance among the materials tested. This table, if you notice, also illustrates how different processing conditions substantially impact the resulting properties of identical alloy compositions. This data is based on different studies in different years and countries. The corrosion of metallic implants progresses rapidly in the human body due to its aggressive environment. Chloride ions in biological fluids accelerate this process, lead to the hydrogen gas production, which can delay healing and cause tissue necrosis. We have the same discussion in vitro experiments. Many biomaterials might take years to degrade in vitro environments, such as PBS or distilled water. So in order to both increase the speed of the experiment and make it closer to physiological conditions inside the body, accelerated environments are used. As a result, for example, a material that takes 1 year to degrade in an aqueous environment can have its degradation behavior observed within 1 week in that accelerated alkaline environment and compared to the other samples under the same conditions. Surface coatings are commonly used to slow corrosion in magnesium implants, particularly in magnesium implants that use in biomedical applications as a biodegradable implants, for example in oral or maxillofacial applications. These materials need to maintain their mechanical integrity initially before gradually degrading and dissolving. Given the poor corrosion resistance of magnesium and its alloys in aqueous environments, achieving sufficient electrochemical durability is crucial. As you notice, the corrosion behavior of LPBF fabricated magnesium alloys varies depending on composition and processing parameters. Corrosion rates are typically higher than cast alloys, primarily due to defects such as porosity and incomplete fusion. But process modifications can influence porosity, affecting both corrosion rates and cellular interactions. Some LPBF fabricated magnesium materials, as you saw in the table, exhibit rapid degradation, which can compromise their structural stability. This is evident in LPBF pure magnesium, which demonstrates significantly accelerated corrosion rate compared to its cast counterpart. And corrosion resistance of LPBF fabricated WE43 alloy is lower than the cast version, with increased degradation due to microgalvanic reactions between stable oxide particles and the magnesium matrix. Surface treatments such as plasma electrolyte oxidation can improve corrosion resistance. Untreated WE43 scaffolds may lose structural integrity within a short period. However, some studies suggest that LPBF WE43 can retain its structure for an extended period with significant strength reduction. Structural factors such as pore size and scaffold geometry play a key role in this degradation rates that we discussed. In contrast, LPBF fabricated magnesium aluminum alloys exhibit corrosion resistance comparable to cast alloys. Some compositions show stabilization of degradation rates over time, aligning closely with cast counterparts. In addition, enhancing antibacterial properties through the addition of copper has been explored, but copper inclusion accelerates degradation, highlighting the trade-off between antibacterial effects and corrosion resistance. Magnesium helps in terms of cellular functions, stabilizing DNA and promoting bone healing. However, the rapid degradation of magnesium scaffolds can lead to the excessive release of hydroxides and metal ions, of course, negatively affecting cellular viability and overall biocompatibility. And furthermore, studies on LPBF fabricated WE43 alloy indicate varying biocompatibility results. In vitro experiments have shown that MG63 cells, of course, kind of bone cells, in direct contact with WE43 alloy initially exhibit cell death as observed through live staining and fluorescent imaging. However, after pre-incubation of WE43 scaffolds in physiological serum for 48 hours, cell viability improves significantly. This suggests that initial degradation byproducts may contribute to cytotoxicity, but preconditioning the scaffolds can mitigate this effect. Cytotoxicity assessments of rare earth-based magnesium alloys indicate that while these materials do not inherently possess toxic properties, their high degradation rate leads to localized pH shifts and hydrogen gas involution, which impair cellular metabolism. It is noteworthy that plasma electrolyte oxidation has been identified as a promising surface treatment to enhance cellular adherence and reduce adverse degradation effects. so it can improve scaffold biocompatibility. In conclusion, the biocompatibility and biodegradability of magnesium alloys makes them ideal materials for biomedical applications. And due to manufacturing feasibility of complex shaped components, it would be possible to fabricate customized magnesium components via additive manufacturing techniques based on patient-specific anatomical data. One of the gaps that still exists, and this article points to it, is this issue, that how the topology of scaffolds affects cell proliferation, new cell growth, and the lattice structure of the fabricated magnesium components. These issues are still unexplored. This suggests that further studies should be conducted using in vitro and in vivo methods for the LPBF magnesium scaffolds. In a nutshell, it is expected that future developments of LPBF process of magnesium, particularly those for bone tissue engineering applications, will focus on a wide range of properties, including mechanical properties, corrosion performance, biocompatibility, printing properties, biomimetic properties, and of course biodegradation properties. It would be a reliable method for building various organs and tissues with diverse mechanical requirements, whether the use of new types of steels as biomaterials with different compositions is being developed. It would also be a reliable way to achieve reprogrammed mechanical properties and functions. The magnesium-based alloys produced by LPBF will be used to make stents, screws, plates, and scaffolds in the near future. So this concludes the review of the article. One very important point is that in these 3 videos, I tried to present the article's content to you in the exact order it was written. But the question of what constitutes the best method for reading an article is a separate discussion that requires its own conversation. In the future videos, I may elaborate more on some of the topics we mentioned. Thank you for your listening.